So in this video, we're going to cover briefly organic chemistry, more specifically how to draw organic structures in a much faster way. We need to be able to know how to recognize these structures drawn in the ways that we're used to as Lewis structures and in the quicker ways as well. So just a quick little refresher, an organic compound, when we're talking about organic chemistry, these are compounds with carbon. Okay. Again, usually they typically also have hydrogen, nitrogen, and oxygen, but any compound with carbon is going to qualify as an organic molecule. An example is propane. Okay, propane gas used in a grill. The chemical formula is C3H8. So if we drew the Lewis structure for propane, C3H8, we would have three carbons drawn, bonded together. We know that carbon likes to bond to itself. And then we would have hydrogens off of each carbon until I have 8 hydrogens total. Just a quick little refresher, we didn't draw them all in a flat line because we know that with molecular geometry, this carbon has 4 electron groups, no lone pair, so this is going to be tetrahedral with a 109.5 degree angle. Just a little refresher there. This is what we're used to doing with Lewis structures. However, organic chemists are a little lazy. They're drawing big, large molecules, so they actually draw these in a much faster way. So what would the faster way look like for the molecule of propane? In fact, believe it or not, what I just drew right there would represent this exact same molecule to an organic chemist or someone familiar with organic chemistry. Now let's think about why. Well, number one, vertices or points equal carbons. So here, let's think about how many points do we have? I have 1 point here, 1 point here, and 1 point here. So there's 3 carbons in this structure, consistent with what I would expect for this formula and consistent with what I have in the Lewis structure. But now where are the hydrogens? Well, since hydrogen is not usually involved in any reactions, organic chemists don't draw atoms of hydrogen. But we know that they're there. And how do we know that they're there? Well, we know that carbon forms 4 bonds. Okay? So that could be 4 single bonds, it could be 2 double bonds, it could be 1 triple bond and a single bond, but we know that carbon likes to form 4 bonds. So all we really have to think about is, okay, how many open bonds are there available? So for example, for this carbon right here, okay, how many bonds can it still form? Well, it's bonded once already to this other carbon here. So therefore that leaves there's 3 places where hydrogen can bond. Same thing on this carbon over here on the right. It's bonded to that other carbon up in the top, so it has 3 available bonds left. Now this carbon here has 2 bonds to the other carbon, so it can only have 2 hydrogens. So essentially what you need to be able to recognize is if I draw or you're given a molecule like this, you have to be able to write the formula. So you'd have to be able to figure out that, number 1, there are 3 carbons, C3, and therefore how many total hydrogens must there be? Well, there's got to be 1, 2, 3 off here, 1, 2, 3 more, that makes H8. Okay? Given a compound, draw its structure, or vice versa, go the other direction. Let's do a couple more examples. Isopropyl alcohol has the formula C3H6OH. So if we were to draw this as a typical Lewis structure, which is what we're used to seeing, it would look something like this. Okay? Apologies, this should be C3H7OH. Okay? We're used to this. Okay? This makes sense. I got angles drawn representing, the appropriate bond angles more or less, but to an organic chemist, how would this be drawn? An organic chemist, again, think about carbons represent vertices. So we kind of have the same basic backbone here, which I've drawn in red. Boom. However, the only addition now is we have this hydrogen an oxygen, this OH group. So we would draw up here O and H. Hydrogens are drawn when they're bonded to atoms that are not carbon. I don't draw hydrogens on carbons. But since this is not a carbon here, this is an oxygen, I draw that H written as is, because it's going to be important in some type of reaction. But again, same thing. I have 1, 2, 3 carbons, because I have 3 vertices here. This is not a vertice, this is just showing a bond to this oxygen. I must have 1, 2, 3 hydrogens here to make 4 bonds. 5, 6, excuse me, 1, 2, 3, 4, 5, 6, 7. So that's my H7, and then the OH. Boom. Let's do another example. Benzene, C6H6. Okay, if we drew benzene's Lewis structure, again, you're not expected to know the structure here. You would be given it, or you'd be given the other one and asked to draw the formula. This is what the structure of benzene looks like. Again, you do not necessarily have to have this memorized until you take organic chemistry in college. But that's the structure of benzene. So how would I draw it with a faster organic structure way? Well, remember, every carbon becomes a vertice. Boom, boom, boom. So there's my backbone. That's the backbone of the structure. So I'm going to have boom, 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 boom to make my 6 carbons, 6 points. But now there's a little difference here. Some of these are double bonds. So we draw those in the same way. We just draw a separate line. 1, 2, 3. Those represent the double bonds. Again, I don't draw hydrogens bonded to carbon. But how do I know how many hydrogens must be on each carbon? Well, think about this carbon right here. It has 1 bond going out this way, 2 bonds going out this way because of this double. So that's 3 bonds already, so there's only 1 left for the hydrogen. And it'd be the same on every carbon. Let's do a few more. Extra practice. C4H10, CH3OH, and CH3COOH. So first, what would these look like? I'll draw the Lewis structures, and I want you to practice drawing the actual OChem structures, organic chemistry structures. So C4H10 would look like this. HH. Okay. CH3OH would look like this. And CH3COOH would look like this. So go ahead and try to draw those as, pause the video and try to draw those in their organic structure form. Okay, so what they would look like for C4H10, here's the carbon backbone. So C4H10 would look like this. That would be it. That is the structure. For CH3H3OH, that structure would look like this. Oop, excuse me. That's not correct. OH. Here's my 1 carbon here, bonded to that oxygen. That's that structure. And CH3COOH, here's my backbone right there. So I have 1 line, and I got this double bond to this oxygen. I got 1 more oxygen with a hydrogen coming off of it. Again, I can add the lone pairs if I want to. I don't necessarily have to. But you got to be familiar with, if I give you a structure like this, write the formula, or if I give you the Lewis structure, be able to draw it in the organic form.